Okay, we're going to turn in the quiz revisions, but not the homework. Okay? Everyone's going to get 20 out of 20 on the homework. You can keep it to study. But we're going to go over it. So we're going to turn in the quiz revisions. Yeah, just fold it up like normal.
Because last year
we're not turning in the written homework. This is just quiz revisions. Quiz revisions.
It's just the opposite.
Redos.
That's all she said.
You can hold on to that homework to study with it. Everyone's going to get full credit for it.
I'm like, what? I know. I'm just like, why? I mean, it's just interesting because right when you just never know. This just further proves that you can go back. You know, last semester when I took this class, we did differentiation first and then integrals, and all she told us about integrals was it's just the opposite of differentiation. And then I had no idea what was going on at all.
This is just quiz revisions coming in. So I want to take a good amount of time to go over that written homework. Okay? Let's do that. Last chance. Quiz redo. So last time we saw that this symbol anymore. We good? Last time we explicitly defined this symbol here. Okay, this is integral symbol. Okay, and integral, when you see integral, do you think, oh, that's talking about accumulation, or is it talking about rate? Accumulation. What kind of function do we take the integral of? Whenever, so you have an integral, the function that you're integrating is what kind of function? A rate function. Okay? Are we accumulating rates? Are we adding up rates, a bunch of rates? No, what are we adding up? Delta y's. So is this y? How do we get delta y? Right, so this is our constant rate of change. Little bits of change from constant rate of change. It all goes back to delta y is k delta x. What's k? It's our constant rate. So when our changes in x get very, very small, they become dx. Okay? Or in this dt. Okay? So, and what we start from where? A. And so what is the meaning of x in this whole notation here? What does x represent? So this is a function, right? So this is our accumulation function. What is the input? What is x? What's that?
The last value, the endpoint.
The endpoint, okay? Can you say it in terms of accumulation? Amos? What's that? Yeah, so at the point up to which we're accumulating. And that's right, it's the end point, it's the last point. So we're starting accumulating at A, and then it's an accumulation function. So we can put in different values of x, and depending on the value of x that we put in, it'll give you the accumulation, what? Up to x. Up to x. So that gives us a whole function of accumulation. So when you plug a value in, so say a of 10, then we get a, so now we're saying from a to 10, rt dt. So this is no longer a function. What is it now? So how would you characterize what I put a box around there? Yeah. Yeah. So be more specific. Yeah, keep going. Which amount that we've accumulated? So what is this saying about what amount are we accumulating? What is this saying? Okay.
Accumulation up to 10.
Yeah, so it's accumulate starting at A up to 10. Yeah, you knew it. You just, yeah. So starting at A up to 10 for an accumulation that has this rate, right? That has this rate. So this is a value now. Okay. Another way we say this is so it's an amount accumulated or it's a net change. Okay, net change in the quantity. How much did the quantity change from A to 10? Okay, so that's kind of just a recap. So this homework was practicing kind of these ideas, practicing integral. And so integral, so exact accumulation or approximate? Yeah, so when things get sufficiently small, right? When our bits get sufficiently small, the integral then is indicating this is our exact accumulation function. This is what we've been working for, right? And so it's the shorthand notation of the long version, right? When things are very, very small, when bits are very small. Okay, so let's go over some of this. So what is R of 8.65?
Exact change of the height of 8.65.
Adonijah, what is it?
Oh, it's the rate of change of the height 8.6 miles from the start.
Rate of change of the height or elevation, 8.65 miles from the border. Agree with that? Yeah, that's what it is. Okay, so now we want to define this elevation function or elevation accumulation function as an integral. So what will, before we do it, what will the input and output of this function be? So before we write anything down. So we're going to create this function e of x. What's the input and what's the output? The meaning.
Well, the input is going to be how many miles you are from the border.
He wants how many miles from the border is going to go into this function. Sharon likes it. Okay? And what's going to be the output of this one? What's that? Accumulated change in elevation. Almost. Accumulated elevation. What are you going to say?
Kind of the same thing, but up to the point we designate we want to stop.
Okay, so is it going to be the change in elevation from the border, or is it going to be the elevation? It's going to be the elevation, okay? So, but we can distinguish here in a second. So, as an integral, what are we going to start integrating at? 0 to 8.65. Will that be a function? No.
X.
We want a function, right? We want it to give us the elevation at any distance from the border. So we're going to x, right? And then here's our rate function. So we're going to change it to something else. So say t. Is that going to give us the elevation X miles from the border?
Plus 2 divided by 100.
And where do you want me to put the plus? I'm going to add it to this?
No.
What do you want to do, Kaiser?
Because it's part of the rate function, isn't it?
This is part of the rate function, so we want to add that to the rate. What kind of thing is this? Is this a rate?
That's 2 divided by 100.
In the
And the
first
rate
function, it says
cosine
plus 2
x.
feet over 100 feet.
Oh, I see. I'm sorry. You're saying I wrote this down wrong. My fault. Okay, now I've got the rate function right. So this 5, this. Okay, there we go.
Isn't there more to it still?
Okay, now is this the elevation? Will this give us the elevation at X miles from the border?
No, they change it already.
There's still more
Right. I'm asking. Will this give us the elevation X miles from the border?
though.
No. So how do I need to change it?
Add your 500.
Where am I going to add the 5,326?
Very good.
Inside?
Outside.
Outside.
You need the hundreds.
What?
It's 2 divided by
Plus
100.
2 feet.
No, this is a unit.
Oh.
This is a unit, right? This is saying that for every, if you put in x equals 3, that stands for 300 feet, and you're going to get the elevation in feet out. That's what this is saying. So this is feet of elevation per 100 feet of distance from the border. So putting in 5 would be like 500 feet from the border. Putting in 7 would be like 700 feet from the border. Okay, so what is just the integral then? What would just the integral mean? Change of elevation from the border. But if we want the true elevation, we're going to start at 5326. And then this will give our change x 100 feet from the border. Oh, x miles. This is what's going on here. X is miles. What is this feet per 100 feet? If it's x miles, this should be feet per mile. I never noticed that. Okay, so sorry if that was confusing. If it's x miles, then the rate should be in feet. Yeah, per month, that's right. So feet per month. Okay, any questions on defining that function, B? Okay, so what is E of 14.289? Yeah, Andrew. Sure, absolutely.
That change, I think it should still be feet per 100 feet because the elevation is measured in how many feet it changed over 100.
Yeah, you're right, you're right. Thank you. Okay, so this is correct.
So we should just be 2 divided by 100 still, or just 2?
2 is part of the
No,
function.
this is the unit. This is not 100 is not part of the function. This is this is the unit. So
What units get output then? If you
what's that?
So what units get output when you multiply feet per 100 feet times miles? The rates in feet per 100 feet, but then our DTs in miles. You have to convert that.
No, your elevation's in feet, and so your y is going to be your feet, and your miles is going to be your x axis.
Yeah, I didn't write this problem, and I've used it before, and I've never come and had this difficulty. So I'll have to think about it more. Because the rate, so per 100 feet. Yeah, so I'll have to think about this more. But so we can still understand the big picture here, right? So are we okay with this? Yeah. So I just need to think more about that. So here we've got this is our change in elevation from the border, and if we want the elevation function, then we're going to start at 5326 and add on our change in elevation x miles from the border. Okay, so if we plug 14.289 into this function, what will we get? elevation 14.289 feet from the border. We're going to get the elevation, okay? All right, so what happened when you graphed AX with delta x of 0.1 versus EX? Did you do that with graphing calculator?
My function is all whacked out. So.
Okay, so here's our rate. So that's our rate function, and we want to set delta x to 0.1, and here we'll just graph the rate function. Okay, so there's our rate function, and then our step function with delta x of 0.1. And then the corresponding accumulation function. So this is the accumulation function based on the delta x of 0.1. This now is going to be our rate of change of, no, sorry, our change of elevation, x miles from the border, as an exact accumulation. So do that black. There we go. So what are we looking at here? So the purple one is, or the pinkish one, is our approximating accumulation function based on this one right here, the long form. And then the black function is exact. Now, this is not the elevation function, right? What is this? It's the change, right? It's the change since the border, so that's why it's starting at 0. So we could add whatever 5326 was it? We could add 5326 to both these functions, and then what would it do? It would just move them both up 5326, and that would be our true elevation comparison. But this is now just change in elevation from the border. Okay. So you were to look at 2.5, right? So why does it say? So this is a nice question. So on the pink one, why does it say at 2.5 not a number? Did anyone run into that? So like if I go a little bit less or greater than 2.5, it gives me an output. But at 2.5, it says not a number. What's going on?
I thought that it was because the black one was exact, and then our estimate at 2.5, so it showed that we were off. So on the exact number, there wasn't anything.
But all of these are off. I can move a little bit here, 2.45. I get a value, and it's still off, right? So here, I'm on the pink one right now, and I'm off the 2.5, and it's giving me a value. But when I put it on 2.5, I don't get a value. This is not a number. Yeah, Andrew.
Since 2.5 is exactly by the delta interval,
Okay.
we don't have a rate of change. Since we didn't define rate of change at the control point themselves.
Yeah, so you remember this thing right here? We had that when we did the step function. It gave us the drool, right? Like, so we had the step, and then we had these vertical lines that we wanted to get rid of. So what did we do? We put holes in the graph at every breakpoint. So as you define this accumulation function, it's defined everywhere, but not at the breakpoints. And 2.5 lands on a breakpoint. So if I take that off right there, if I delete that, now we should get something. There it is. So now on 2.5, I got the number 5.94.
Then how come the vertical lines don't exist on your step function?
What's that? Because this isn't the step function. This is the accumulation function.
But the lines aren't back.
Right, because this is the step function.
Oh.
So if I were to, I still have the step. Oops.
Oh, it's still up there in the step.
In the step function, I still have that not equal to thing.
Only in the.
So in our
So if I took it out of the accumulation function, and now I'll get the values at the. Yep.
gotcha.
Make sense? Okay, so at 2.5 for the approximate, I get 5.941. And what does that mean? What is that?
The change in elevation.
So 2.5 miles for the border,
It's going up 5.941.
we're 5.94 feet higher than at the border. Okay, and then I could put it on the actual. 5.819. Okay, so the actual then, based on the integral function, that's the black one. This one here is the, and there are the two values. So I was doing it by tracing on the graph, but you can just in graph and calculator put f of 2.5, a of 2.5. There are those two values. Okay, so this delta x of 0.1 miles is still a large enough difference, still a large enough interval width that we see the difference in the functions, 5.8 versus 5.9. So if make delta x smaller, what will happen? Which one will change if we make delta x smaller? A, and it'll get closer to the f value, right? Which is more accurate? E, right? Absolutely, E is more accurate. It's because that's based on the integral expression that we wrote. Any questions on number one? Any questions on number one? Okay, how about number two? So back to our weight. This is the same one that we worked on in class a couple times. So let's write the exact accumulation function of weight. Now I'm telling you the weight begins at 11 pounds. So let's see, somebody new. Lauren, did you get this one? Part B, 2B? So we're going to call it WX. Do we know what A is? Because what is, now what, okay, so before we're going to do this, what is our input and output for this function? So what does X stand for? Time in minutes. So really, by this value of A, is it have to do with a weight or a time in minutes, this value A? And do we know that? So does that have to do with the weight or time? Time. Do we know the starting time? Yeah, 0, right? We're starting at 0. Okay, and then the output will be the weight on the scale. So from 0 to X. Lauren, keep going. Can you tell me what R of T is? So what do you want up here? But R of what? Yeah, so if it's R of T, we want T minus 1. Then? Okay, what's just the integral mean? The change in weight in the first X minutes. And the whole thing together then is? The weight after 10 minutes. Okay, and make sure that 11 is not inside the integral, right? Okay, questions on that? Does it make sense? Okay, how do we say this? We say the integral, so this is the weight, accumulating weight function, is the integral from 0 to x of r of t dt plus 11. So again, the integral from 0 to x, rt dt plus 11. Okay, so this part D is a really nice question here. How can we represent, so we got two different functions going on here. We've got our rate function, we've got our W function. How can we represent the change in weight from 0.75 to 2.34 minutes in two different ways? What's one way we can do it? Somebody new? Helios, you got one way we can do this? Represent the exact change in weight.
I'm not sure, but is it LVD 2.34 minus W 0.7?
Does that give the change in weight from 0.75 minutes to 2.3 minutes? Yeah, nice. Good. Other way, DJ. Integral? We want exact, right? So if we're doing exact, it's got to be integral 0.75 2.34 of yep. Exactly. RT dt. Okay. Plus 11, right? Oh, you're saying no. Why not? Why not plus 11? Okay, good. Anthony, were you going to say something? Yeah, sure. So this good. So this is the change, the net change from 0.75 minutes to 2.34 minutes of a quantity whose rate is this, right? And this quantity is weight, right? So we don't want to add the 11. We don't want to add the 11. This gives us that net change. Questions on number 2? Do we need to graph it, or any other further questions on that one? Number 3. Integral. Somebody new who wants to define this integral. So because we want it to be in seconds, we'd rather have this thing in miles per second. We'd rather have it in miles per second. So how can we start by changing this? He wants to divide the whole thing by 3,600. Will that now be in miles per second? Yeah, that's it. And this is fine because x is already in seconds, and that will calculate the miles per second. Okay, so an integral, the number of miles the meter has traveled at every moment during the first 20 seconds it reached the Earth's atmosphere. Somebody new. David, did you get this one? You did not? What's that? So can you do it on the fly here? How can we write an integral that'll show the number of miles that's traveled every moment during the first 20 seconds? So we know there's an integral because it's saying it's an integral, so. Zero, 2. Okay, do we want 20 here? It shows the number of miles the meter has traveled at every moment. What is that implying? Yeah, it's a function. It's just that they're limiting by saying during the first 20 seconds. They're just saying x is going to be what? less than or equal to 20. So that's all they're saying by this. So if we want to know how far it's traveled at every moment, that's a function. We need that number of seconds to take on different values, to vary. What am I going to put here? This sucker right here. X squared? Something else. I'll just for how about v squared? Is it okay? Then what is this going to be? dv. So there's nothing magic about t, right? It's just these have got to be different. So am I going to add the height of the atmosphere to this?
No.
Why not?
Because you're tracking how many miles it went.
Yeah, so this listen to what it wants. The number of miles the meteor traveled. The number of miles the meteor traveled. So we're not going to have a starting value. The accumulations will start at 0, so we're not going to add anything in this case. Lauren?
So the X of the calculator,
Uh-huh.
couldn't you just put 20 there? Would it be the same thing?
No, because it says at every moment. So we want to show us the number of miles the meteor has traveled at every moment. So it's not saying the accumulation, or it's not saying how far it's gone in the first 20 seconds. It wants to know at 1 second, at 1.5, at 6.8, you know, all these different. So this is all this means here is that we're going to limit x just to being less than or equal to 20. So it's still a function. So we call it distance function. Other questions?
So if
Okay.
you put the 20 there, it'd just be a value.
So what would it mean if we put the 20 in for x? If I put 20 there instead of x, what would that mean? How far it went in those 20 seconds, right? It would be d of 20. It would be d of 20. You'd be getting a value now rather than a function. Okay. So how far did the meteor travel in the first 10 seconds? How would we represent that? How could I represent that? D of 10. Okay, let's actually do this. So here we have this thing that graphing calculator understands and can do the work for us, right? So we haven't learned an algebraic way to calculate this, but we're using graphing calculator to do it. So let's do that. So let's put this in. So d of x equals 0 to x of and let's use v. No, actually, that's v is reserved for something special in graphing calculator. So we'll use q. Great. All over. And then we need d q. Okay, and so if I want to find how far it's gone in 10 seconds, what am I going to do? D of 10. So what is the meaning of that? Miles per second. It's going 40.38 miles per second. Is it right? Yeah, what is the meaning of our function? What is it telling us? Just miles. It's traveled in that miles traveled in 10 seconds. So since hitting the atmosphere, 10 seconds later, it goes 40.39 miles. Next question. How far did it travel from 15 to 20? How can I get how far it went from 15 to 20 seconds?
Put 20.
I could do d of 20 minus d of 15. How else could I do this? What could I do? I could do this, right?
We'll put 15 and then add 20.
And I could do 15 here. 20 up top. It ought to give me the same value. Good. It worked. So 2 different ways to represent that change in distance from 15 to 20 seconds. D of 20 minus D of 15, or the integral from 15 to 20 of the rate dq. Questions? This is making sense? What's the last question?
How many seconds after reaching the Earth's atmosphere does the immediate crash into the Earth?
So let's do that. How can we make sense of that? So what are we solving for here then? So we've got our distance function, and they want to know how long did it take to crash into Earth. So how do we make sense of that question relative to what we've got for our function? Tyler.
As the distance increases, we want to know how long it takes until it reaches the full distance of
Okay.
the Earth's atmosphere.
Okay.
So, I went and said the atmosphere is 258.514 miles thick. So if you do that minus the effect, it's 0. That's when it hits the atmosphere.
What is our unknown here? What is it that we're trying to find? So Q or X?
Are we trying to find the value of x when the answer is 0? So like
So you want D to be 0?
right.
So is this height above the ground? Is D height above the ground? So that's what you would be saying. If you're saying 0, you're interpreting the function as D is giving you height above the ground. Is that right? Now remember what D is. What is D telling us? Distance traveled since it enters the atmosphere. Yeah, Dan.
Couldn't you just put that this is from the atmosphere to the ground? X?
In for X?
Yeah.
So he wants to put the distance of the atmosphere in for X. What does X mean? X is time, right? Rohit. So you want D to be the height of the atmosphere? And then what are we looking for? We're solving for X, right? So algebraically, we don't know how to do that, okay? We haven't seen any algebra associated with this expression. So what's an alternative that we can use to solve this? Okay. Got this wonderful software. What could we do? No, we got the exact accumulation. Graph it. So we can say y equals d of x, and it's and we want it from 0 to 20 seconds, right? So 0 less than x less than 20. And what do we want to know here? What time it hits. How do we make sense of this graph to figure out what time it's going to hit the ground? What is our, so we got to know what our quantities are. What is, on this x-axis, what is the quantity? Time in seconds. Since crossing the boundary of the atmosphere. What is y? Distance traveled in x seconds. So How do we figure out how many seconds it takes? What are we going to do? What's that?
We need to know how high off the ground it was.
How high off the ground it was. Can you be more specific? What do you mean?
Like the meteor, it's like we can see that like at an X or a value of the time, we know how far it traveled, but we don't know when the impact of the ground is.
Okay. Yeah, Tyler.
Couldn't we find the thickness of the atmosphere so we know how far it needed to travel?
And would that be an X or a Y value?
That'd be Y value.
Okay. The height of the atmosphere would be Y.
So
Yeah.
couldn't you have the height of the atmosphere minus d of x? So it's going from that height down until it hits the ground or the x-axis.
What'd you guys find as the accepted height of the atmosphere? You had to look that up.
I found 258.514 miles.
62. Yeah, 62. So 62 is the height of. There's different layers, okay, but this is kind of an accepted distance from the Earth. Yeah, so if it was 258, something would be totally wrong with this function, right? So kind of as an accepted height of the, or distance to the edge of the atmosphere, 62. So now what? Huh. It's not giving me some. It's supposed to pop. Click on there and pop on there.
60, back to 60.
Yeah. All right, that's the best we're going to do. So the ordered pair is 16.1875 and 62.03. What does it mean?
After 16 point whatever seconds,
So just over 16 seconds. That's how long it would take.
That's assuming it's like directly perpendicular to the atmosphere. It's not doesn't have
That would change.
Distance traveled. Right. So that it's flying straight down. That's true. That's true. Yeah. Yeah. So that if it were on an angle, the distance function would just be giving us distance from the edge. Does that make sense? So like vertical distance. Whether it's going sideways or not. Yeah. Yeah.
Either way, like there's no way to push seconds at 0 because we know 0 seconds it has to collide with Earth because it started.
What, no. Marcus, what is the? You gotta always keep in mind. You can't forget what is the input and output of this function. What's the input and what's the output? What's the input into this function? What is x? Time since when? Time since entering the atmosphere. And what is the output of this function? Distance traveled. Okay? What you just said reflected that you thought that the output was elevation above the Earth. You wanted to put x equals 0 in. And that x equals 0 is when it's entering the atmosphere, not when it's hitting the ground. You see? So we need the time when the distance traveled reaches 62. So we want the x value when the distance traveled is 62. Not x equals 0 means distance traveled is 0. That's what you said, x equals 0. Any questions on this problem? Okay, I'm not looking forward to this. Okay, how did this go? Anyone think they got it? Somebody new, want to give it a shot? What'd you put? How about this Daniel here? Did you get it? Blue shirt. Yeah. Didn't get this one. Tylea, did you get it?
Well, I wrote something. I don't know.
Okay, let's we'll fix it all together.
I wrote a of x equals to, then I have the summation.
Yeah.
C equals 1, on top it has x minus 0 over dx.
Okay, we're gonna need the floor function, right?
Yeah, sorry.
Of what now?
Of x minus 0 over dx.
X. Okay, good.
And then I put, for the R of t, I put sine t.
Sine of.
And that's the part that I'm not sure I did right. I put 0 plus k minus 1.
A minus 1.
Dx.
Dx.
Dx again.
Dx.
And then plus sine left of t.
Left of x, right?
Oh, x, yeah, sorry. And then times x minus the left of it.
All right, she's offered something up. Want to change it? Comments? Is it what you put? Or did you put something different? Totally different.
No, mine's wrong.
Oh, you like this better?
Yeah.
Tyler?
Do we need the plus side left x at the end since the intervals are so small now?
Okay, that's a good question. So he's saying, since the intervals are so small, do we need to have this last little piece? That's a good question.
I would say no, because that little piece adds for the overflow of the leftover part, but since it's so small, that leftover part might be.
You could argue it either way. You could argue in this form, in the summation form. You could, yeah, your argument. You could argue that if dx is our atomically small, then this basically becomes 0. But because it's our accumulation form, we'll just put it in there so we remember it. How about that? But yeah, good question. Other comments or so she nailed it. This is right. This is perfect.
So A gets turned. You just put your starting.
Well, it is. A is 0, right?
Okay.
Starting 0. Okay, again, make sure as part for your studying for your exam, you know what everything means, down to every detail, all the way up to the big picture of it. Okay, I want to. Any more questions about the homework? Okay, so if you noticed in my email, I talked about the first My Math Lab assignment. So I want to just show you that real quick. If you go to My Math Lab, if you click on homework, you'll see this. Okay, this is the first one, February 20th. So actually, I changed it. It's due Monday morning. It's not, normally this will be called what the due date is. I forgot to change the title, but I did change the due date. It's due Monday morning. But all the questions, there's 5 questions in there, all pertain to exam material. So just do it before the exam, and then it'll help you with your studying. And then you won't have any homework over the weekend. Okay? So let me click on it. It says that you get, see here it says number of times you can complete each question, 1. Okay? But what that means is that really for each time you can complete it, they really give you 3 tries. Okay? They really give you 3 tries at the correct answer. So if this said 2, you'd really have 3 tries on one type, and then they give you a similar problem again, you'd have 3 tries again. So this just means you're going to get one problem, but you're going to get 3 tries on it. So let me just show you that. So click on question 1. This one's matching. We'll go on to the next one. One where you're actually putting in answers. Okay, so the zeros of x are approximately 50 and -4. Okay, so I'm going to put that answer in. Oh, I can't do it till, okay, so the accumulation x equals approximately pi, and I'm choosing answer D, okay? So now I'm ready to check my answer.
All of them are correct.
Right. Okay, so it says, sorry, not correct, okay? So then it gives you a little tip. You're going to have to, the tip is from the textbook. It doesn't know the curriculum that we're learning, so this may confuse you, so I would just ignore it, okay? Think about what we've talked about. So now you should be able to try again. Once you hit done.
So it won't tell us if we got a portion of
Right.
it, right?
So now you come back. Okay, listen up. Now you come back and you try again. Negative 100, 8. This would be my second try. After the third try, you won't be able to change it anymore and get credit on it, okay? So this is all relevant. You got 5 questions, all relevant for the exam, but not due till Monday morning at 10 a.m.
Right.
We don't have, it saves it right from there, right? We don't have to print
You don't, yeah, it all saves it electronically in the computer. Okay, so you got your exam tomorrow. If you need help, please email me or come to office hours tomorrow. Same routine for the exam. Downstairs, bring your Sun card. Be in the door by 6:30.
Can you post this video right away too?
Sure. I'll post this video. Oh, and then I'm going to post all the quiz solutions, and I'm going to post several homework solutions from the last month as well. They'll all be where you got it originally. Hold on one second.